Good evening, everyone. Welcome to TACO After Dark. My name is Brett Zerba. Wait a minute. What do you mean, Brett Zerba? This isn't John Barba or Dave Holdorf or Rick Mayo? No, this is the commercial team, Brett and Rich.
Hey, I'm as confused as anybody.
Well, welcome to TACO After Dark. Let's learn some things tonight and let's have some fun. Again, my name's Brett Zerba. I'm an applications engineer / trainer at TACO, more focused on the commercial side of the business. Today's presenter is going to be Rich Medeiros. Rich and I work together quite a bit, and I recognize quite a few names on here. So I know you've sat through some of these classes before. Our goal tonight is to teach and to have fun and to learn and actually, hopefully, get a lot of questions, because that's what's really going to make this presentation and the first hour and maybe the second hour much more learning for Rich, myself, and anyone else on here, as well as you guys. So please, please, please ask questions. And before I get too far into it, hopefully a few of you can wave your hand that you can hear me and see the great screen that we have presented there. Adam, my friend Adam Olson. Hey, Adam, how you doing? Oh my God, it's been so long. Like Rich and I were able to go to the factory a couple of weeks ago, and I hadn't been there in at least 18 months, for God's sakes. Imagine that, in Cranston, Rhode Island. I'm only not that far away. But as most of you know, TACO is a privately held company. Started by the White family. Third generation currently owns the company, Johnny White Jr. And there he is in the bottom right-hand corner. Quite a guy. I recognize quite a few names on here, and I know some of you have met him or seen him at different events or whatnot. But he is something else. He's quite a guy. And that's his son in the middle picture with a mask on, so you don't get a good view of him. And his son's wife, John III, and Caitlin, and their new baby, Madison, born April 9th. So there's the 5th generation White. Pretty exciting. And I think if you look close, you can see the smile on Johnny's face. And this picture, this screen, is actually from the facility. When you go into the facility, that's actually on one of the screens there, on one of the monitors. And I know quite a few of you have been to the facility, and hopefully by fall or maybe next year, more of you can come to the facility. That's our goal. So anyways, again, let's learn, let's have some fun tonight. And ask questions. I'm going to be monitoring the questions. Rich will be doing the presenting. You know, some of you may have sat through some of the residential after darks with John, Rick, and Dave, and they do a heck of a job. Their following is second to none. So we have a little catch up to do here. And it was very nice of them to give us the summer break period for us to do some classes here. But hopefully we can get some momentum from this and maybe do some others down the road. And as a matter of fact, the leader of our group, John Barba, is online. John, you want to say hi to everybody and welcome them as well?
Thank you, Brett. Absolutely. Welcome, everybody. And thanks for joining us for TACO After Dark, the commercial sessions. This is a little bit different for those of you who may have been to some of the residential sessions. You kind of know how this goes, but for you new folks, if this is your first night school, let's let our hair down, man. Be a little bit informal, and as Brett said, have a good time as we learn. One thing, the questions are ultra critical here, so we want to make sure that we're delivering the material that you want, and no question goes unanswered. And as we've done with our other sessions, we'll stay on, for as long as you guys are here to answer whatever other questions you might have once the presentation's done. Happy to do that. And I think, and there you go, Brett and Rich. I just wrote a check for you guys to cash. But if everybody out there could do me a favor real quick, just so you guys know how to do this, if you could just type in a hi, hello, how are you? in the question section. So I know everybody knows how to do that. Okay, there should be a little question mark thing on your control panel, and you click on there, and you'll go down to the little chat section and just type in a question and let us know where you're from and what's going on in your life. And that's terrific. Great. Oh, so many people are chiming in, so really appreciate that. I'm going to let you guys get back at it. I think someone tried to make me a presenter, but I'm going to turn it back to you guys.
Wrong person. Oh,
yeah. You don't want to make me the presenter. I think you want to make Rich the presenter and go get him. So I'm seeing a lot of people from all over the country here and even up into Canada. So thank you guys so much for the gift of your time this evening. We're really excited about this. And with no further ado, we're going to turn it over to the man, the myth, the legend, the one and only, Mr. Rich Medeiros. Go get him, buddy.
So thanks, John and Brett. Brett, do you have a couple more things you want to say before we get started here?
No, I think I'm all set, my friend. You should have the screen, so take it away.
Hopefully you can see my introductory screen. I've got Taco After Dark up here. And
that's quite a drink you have there, Rich.
Well, I was just going to say that. Dave Haldoff, let me see if I can show my picture up here. Can I?
It's a Taco Teeny, is what Dave told me.
Can you guys see me okay?
I can.
I'm going to kind of shrink this down just a little bit so we don't take up too much of the screen here. There we go. So, yeah, I wanted to find out, Dave made this great graphics for us, and he put the, the after hours cocktail on there. So Dave, what is this drink? What is it supposed to be? I mean, you're the connoisseur of fine spirits. And
Taco Teeny, he said. Taco Teeny.
Taco Teeny?
TACO-TINI. I mean, Taco Teeny.
Well, there you go.
It's appropriate.
It is good stuff, yeah. So I'm trying to make sure I get my pen thing working here. And it's always interesting to see how these graphical things work. Just when you think you have figured it out, there's always some twist to it that you haven't figured out. So hopefully we can get this pen thing to work here. So we'll go right into our discussion this afternoon. But before we do that, I'd just give you a quick intro to myself. For those of you who haven't met me, my name again is Rich Medeiros. I'm one of the senior systems engineers here at TACO. And my background is mechanical engineering, and I am registered in a couple of states, so I'm a professional engineer. I've been doing it for a couple of years, and I've had some fun at it. I specialize in the design and engineering design of HVAC systems, and I did spend the majority of my career on the consulting side of the industry. So in some cases, I might have been doing some of the work that you folks have been doing out there. So hopefully we can get lots of questions going. So let's see what happens when we press the next button here. Actually, we got to press a couple of buttons apparently. All right.
Bingo.
So we're going to talk a little bit about pump curves. We'll talk about pump selection, and we'll talk about Project Builder. And as Brett and John said a minute ago, it's all about the questions and the answers. And we plan on making the presentation just under an hour, maybe a little bit less, and then open it up to questions. And we plan on staying here as long as you guys want to participate in with us. So some of the stuff we're going to cover will include, I'm just going to go down the list quickly here just to kind of get everyone oriented. So we're going to talk, excuse me, 1 second. Hold on, don't go away. I've got to have a little swig of.
We presume it's water, or is it a Tacotini?
No, it's it's water.
Believe it or not, Rich, a couple of our guests knew the name of the drink. They typed in Tacotini.
Really?
Yeah, I'm gonna have to order it the next time if I can ever get into a bar again.
So we're going to talk a little bit about pumps, flow, and head, then BEP, which stands for best efficiency point, non-overloading, horsepowers, efficiency, net positive suction head, all these great, wonderful pump things. If anybody that's gotten to know me know that, I just love doing this stuff, and I stay up nights dreaming up all different ways of doing it. We'll talk a little bit about system curves, variable speed curves for pumps. We'll talk about shutoff head. You've probably heard that term. Some of you might even have heard it referred to as dead-headed pumps, shutoff head. Impeller Trim, DOE, Department of Energy, HI stands for Hydraulic Institute Ratings. We'll talk about the effect that propylene glycol has on pumps and selections and stuff like that. We'll talk a little bit about parallel pump curves, project builder. And I think that's, oh yeah, and then we'll have questions. And as Brett and John said, type your questions. Brett will ask me to pause periodically and we'll answer your questions in real time. We won't wait till the end. Make it as informal as possible. And we might even ask one or two of you to unmute yourself when we get to that point. So let's go.
Hey, Rich,
Yeah.
before you could go too far, I'd like to mention to the crowd, I got a little housekeeping here. Tomorrow, roughly 24 hours after today's presentation is done, you should receive an email with access to the recording. This is being recorded, so you'll have access to the recording and access to a PDH hour, 1 hour certificate if you would like. I apologize for not mentioning that earlier, but nonetheless, take it back away, Rich.
That sounds good. So before we get into some of the sort of engineering and technical stuff, I wanted to go over some pictures of what these pumps look like.
I love green pumps, Rich. I love green pumps.
I know.
That's the best color for a pump.
I think that the one on the left is kind of a what do they call it? Eggshell green, and the one on the right is more of a gloss green. I wonder if we're switching over to are we making them more glossy these days? I honestly don't know.
Especially for pictures.
Especially for pictures, yeah. So let's talk a little bit about what these pumps are all about here. Hold on, let me just gotta try to. I always have to get used to these little extra buttons. All right, let's try it one more time here with the pen. Okay, so the one on the left, as the name indicates, it's an FI. That's our model designation. It's called an end suction frame mounted pump. And it gets its name because the suction side of the pump is at the end of the pump. Well, that's pretty obvious, isn't it? And the discharge is right up here. And as it turns out, if you kind of extend these lines down like this and then over like that, we realize that there's a right angle in there. And when it comes to end suction pumps, the discharge is always at a right angle from the suction. A couple of other sort of interesting things. If the suction, and I happen to know this because I was looking at a pump the other day, one of our models has an inlet of 2.5 inches, 2.5 inches on the inlet. That's the size, flange size. And then on the outlet up here, it's 1.5. So you will find that the overwhelming majority of manufacturers, including Taco, when it comes to an end suction pump, the inlet is always larger than the outlet. That makes the pump a little bit more energy efficient when it's done that way. So here's the pump. I'm not going to go into a lot of detail about the pump, but I want to point out a couple of things because this will come up in our general conversation. Here's the electric motor over here, pointing to that. And then we have a shroud that covers the coupling because the coupling is rotating. So if I make a little sketch down here at the bottom, if I kind of make a sketch of the motor shaft on the left and then the pump shaft at the right, picture those two shafts, they have to be aligned within 5 thousandths of an inch. 5 thousandths, that's 3 zeros. 1, 2, actually it's 2 zeros and a 5, right? Did I get that right?
That's a better count.
5 thousandths of an inch?
So the first digit is a tenth, then a hundredth, then a thousandth.
Yeah.
I remember that from 5th grade math, or maybe 3rd grade or 4th grade or 7th grade. I don't remember.
You know, even at this point in my career, I constantly mess up on where the decimal point would be. That's why I always have to count and ask someone, did I put that in the right place? So
You start getting out to
5,000ths of an
10,000.
inch. So this is the motor shaft over here on the left, for example, and this is the pump shaft over here on the right. And they have to be aligned within 5,000ths of an inch. And then we put a flexible coupling, a little flexible coupling connecting the two. And so because we have two independent shafts, this is known as a split coupling, which means that we have two independent shafts. We also have an end suction pump that uses the electric motor shaft connected directly to the pump shaft. There is no coupling, and so we call that direct coupled. So we can either have a split coupling or a direct couple. So in this picture that I've shown you, this is an end suction frame mounted pump. And the reason we call it a frame mounted, well, because we have a frame down here. And this frame, if you look very carefully, you can see the pump is bolted to the frame, but this little guy right here is actually a drain pan. And we offer those drain pans as a standard feature on our frame mounted pumps. And it might be difficult to see in this photograph, but there's a place that you can connect a pipe right over here in the corner, so that if the pump should drip or leak a little bit, you can actually run that pipe connection to a floor drain. So let's say I'll put a floor drain here. And that way you don't have to have water going all over your mechanical room floor. Now, the reason I point out that the pump is bolted directly to this pan, which ultimately is connected to the frame, the motor is actually shimmed. And you can see the shim right here in the photograph. So when they align these motors to the pump shaft, the motor shaft to the pump shaft, like I've indicated down here, at the factory, they're actually, the pump is fixed, but the motor is the thing that is moved up, down, left, or right, or at an angle in order to achieve the 5,000ths of an inch of alignment. So those are some things to kind of keep in mind about frame-mounted end suction pump. By the way, and tonight we're talking about commercial equipment, and you know, John, Dave, and Rick cover a lot of the smaller pumps that not only do things like residential, but the light commercial. But for tonight, we're talking about the larger pumps. So although commercial pumps can go down to 1 horsepower, for tonight's discussion, we'll say that most of our stuff is 5 horsepower or greater, 5 horsepower. So this little guy on the left here, this end suction, frame mounted end suction pump, we'll assume that it's 5 horsepower or greater. Now, one last thing I want to point out, if you'll notice, there's kind of this void space in the frame. And when these pumps are physically installed at their final destination, we have in our installation manual that this void space should be filled with grout, which is a kind of a liquid concrete. And that stiffens the base and allows the pump, motor, base assembly to be very stiff, and then it minimizes the transmission of noise and vibration into the building structure. So, Brett, do we have any questions out there on my quick overview of an end suction pump?
We do, Rich. And actually, Bill asked a couple of great questions. Before I get to Bill's questions, though, I do want to mention where the pump is mounted to the drip pan. You can see some bolts there. They're actually threaded into a receiver, so there's nothing underneath that you have to lock them into. They're not a nut and bolt setup. We actually, I think they're called PEM nuts, are mounted in there, so you only have to go down from the top. So just keep that in mind. Just something, a little tidbit of the base as well. So
yeah, that's a good point. We get the bases and we bring them into the factory, and we have CNC machines that actually drill and tap these holes or add the nuts to them. So it's all machine controlled, very precise.
So the question was, a couple questions here. How do you align? What's the actual process to align the shafts?
Well, as it turns out, in the factory, we actually use a straight edge to align the two shafts. And again, remember the pump shaft is fixed. So really what we're doing is we're moving the motor around a little bit to align it. But we do recommend that after the pump is physically installed and bolted down to its final destination, that the pump motor assembly be realigned. But when they do it in the field, they typically don't do it with a straight edge anymore. They usually do it with lasers. So they do a laser alignment technique when they get it out in the field. And, that's quite accurate. And it's important because if the two shafts aren't aligned properly, then think of them as running at an angle. Well, if it runs at an angle, then the flex coupling flexes continuously. It builds up heat. It robs some of the energy away from the motor and makes the pump a little bit less efficient and can create noise and vibration. So alignment is critical. And then the other thing that we like to point out all the time is, well, when it leaves the factory, yes, it's aligned, but then we put it in trucks, and then the trucks go over roads. And if you happen to be in New England, we hold the record in terms of having potholes. And, it doesn't take much of bouncing around and stuff to make the motor out of alignment ever so slightly. So yeah, we do recommend that the alignment is done again when it's finally installed in the field.
And just to add to the alignment statement, all of the TACO reps, that word "all" always gets us in trouble. Have the capabilities of providing that service out in the field for our pumps. So just keep that in mind.
That's right. Good stuff. Any other questions, Brett?
No, I think we're good.
Okay, so the next one, the next pump, by the way, just for general information, the end suction frame mounted pump is the most popular pump that we manufacture. We manufacture more end suction frame mounted pumps than any other style. Now, having said that, the pump on the right is called a vertical inline, and this is the second most popular pump that we manufacture. And as it turns out, the vertical inline pumps are gaining in popularity year over year. So I wouldn't be surprised in a few years down the road that the vertical inlines would surpass the frame mounted end suction pumps in popularity. So let's point out a couple of things for the vertical inline. We call them the KS vertical inline. Here is the electric motor on the top, and then we have this adapter in the middle, and then the pump at the bottom. And the adapter is actually a machine fit between the electric motor and the adapter. That's a machine fit, those two devices. And between the adapter and the pump is also a machine fit. So, and even though the electric motor, I'm going to draw the shafts again in vertical position, the electric motor shaft is coming down from the motor, the pump shaft is coming up from the pump. But because it's a machine fit, it's already aligned, and it's aligned within 0.005 of an inch. And because all three components are machine fit and bolted together, they do not require alignment in the field. Now you can see, by the way, we do not have a flexible coupling. We have a fixed split aluminum coupling. And I'm going to kind of draw a gross coupling here on the right, but you can actually see it. There's usually a grill that blocks it, but the grill's taken off so you can see it. There's that aluminum split coupling that connects the two shafts. So all of these components are machine fit, which means they do not require any alignment. They're very precisely aligned because of the machining that's done. And the pump gets its name because if we put a pipe over here on the suction side, there's let's put a little arrow flow of fluid, and a pipe on the discharge side over here, the pump is in line with the pipe. And so that's where it gets its name. The motor is mounted vertically, so put a big V up here. It's mounted vertically, And so that's where it gets its name. It's a vertical inline. Oops, I got the arrow going in the wrong direction over here, Brett. Look at that. Let's erase that.
We've seen that too. That's the,
Yeah.
unfortunately.
We've seen people connect the pump in the field and try to put the suction on both sides of the pump. Kind of put a little pipe connection thing here. So yeah, so the right side is the suction side. You know how I can tell? Well, I can tell because it goes, the casing of the pump goes underneath the impeller. The impeller is actually inside here, and it looks a little bit like this in section. So the water flows down through and then up and then you can see the volute over here, and it comes whipping around the volute and zingo out to the left there. The zingo, that's a technical term.
That is technical. Don't.
Yeah, I think it's a pump term. Zingo.
Actually, you know what? I'm going to take a picture of that drawing right there and put it as a detail on my MEP prints.
Yeah, you should. That's these are highly what do they call them?
Who says you need
Highly
Revit?
scaled
You don't need
drawings.
Revit or CAD. I got this.
Yeah, I know it. Yeah, my manual CAD skills are like second to none. There's nobody that does it the way I do it. Thank God.
Thank God.
Thank God. So that is a vertical inline, and so a couple of advantages of the vertical inline. Generally speaking, they take up less floor space. You can kind of see the amount of space the frame takes up for the frame-mounted end suction, and how little space the vertical inlines take up. And as I mentioned before, I'll repeat again, is that they do not require field alignment, so their installation is much faster than it is for an end suction frame-mounted pump. Good stuff, good stuff. Any questions about these two guys?
Actually, we do have a couple questions. Let's see. What kind of seal assembly is used on the vertical inline pump?
Well, as
It's
it
an
turns
internal
out, the
seal.
vertical inline and the end suction use almost the same type of mechanical seal. So yeah, they both use mechanical seals as opposed to a stuffing box. In fact, I believe all of our commercial pumps use mechanical seals, and if somebody wants a stuffing box, I think that's an option, but we don't offer it on the end section or the vertical inlines. In a minute, I'm going to show you the larger pumps. And the larger pumps, I think, especially the horizontal split case, can be ordered with a stuffing box, but they come standard with a mechanical seal. And we get our seals from John Crane Seals. So hopefully that answers that question, Brett.
Yeah. Okay. Oh boy, we just opened up we got questions up the wazoo here, so let's get going.
Is that another technical term?
Yeah, that is a technical term, especially after 7.
Yeah.
I assume it's easier to change a seal on a vertical pump than a horizontal pump.
Well, as it turns out, in this particular case, the pump on the right is called a KS, which is a vertical inline split coupled. We do manufacture a KV style pump, and that's when the electric motor shaft is actually bolted directly onto the impeller. So the one that we're looking at, you can actually undo the bolts. You can see the 3 bolts here for the vertical inline, and you can take the split coupling apart, and then you take these bolts out, and then that gives you access to the mechanical seal. So you can service the mechanical seal without disconnecting the pump from the piping system and without removing the electric motor. You can service the seal on a vertical inline. You can actually do the same thing. I don't have a photograph of the backside, but you can barely see it. The bolts here, this is called the bearing frame. The bearing frame can be moved or pulled out from the backside of an end suction pump. So you can unbolt the electric motor. Sometimes you have to push the motor off to a side, disconnect the coupling first rather, then loosen up the electric motor, twist it to the side. Then you can remove the bearing frame and service the mechanical seal again without unbolting the pump from the base and without unbolting the piping from the pump. So in both cases, the mechanical seal can be serviced quite easily. Hopefully that answered that one.
Yeah. So there's a couple of questions that center around supporting the vertical pump. So let me try to help out answering some of this. because we talked about this yesterday on Take-O Tuesday.
Yeah, we did.
The different sizes of the vertical pump can be supported just by the pipe hanger. Others should be supported from underneath, and underneath the pump where that suction goes into the pump, there's actually a machined surface with holes, threaded holes in there, so you can actually bolt, set it on something, or bolt a Take-O supplied option a stand to them as well. But at no time should they're different than the base mounted pumps. They should not be physically attached to the floor. You really need to get more information. You need to read the I&O manuals, and maybe we can cover that as we get further into the presentation. But these should be kind of free swinging, but up to 10 horse, yeah, maybe 10 horse. I've seen them mounted just with the pipe hangers, holding them up as long as they're sized correctly. So they're a little free floating, and we do have the version that's direct coupled as well. That's our KV model. So there is no split couple. So maybe for us, I was talking to one of my good friends today from Emerson Swan, Jason Bissett, and he recommends KV pumps for 7.5 and below horsepower, and they could just be mounted in the piping and being supported by the pipe hangers themselves. So there's all, to answer that question quickly is not easy. It's a little more difficult, but nonetheless, I'm sure I confused everybody, but back to you, Rich.
Well, I've shown one method that you described, Brett, and that's where you have hangers on both sides of the pump connected to the pipe, and the hangers are connected, and they have to be rated for not only the weight of the water, the pipe, but also the pump. And that's one way. And then the other one that you mentioned is when we actually, you can purchase a stand from us that goes at the bottom like this, and it bolts to the bottom of the pump, and that stand can sit on a housekeeping pad. And depending on the strategy that you use, most of the time we put a neoprene pad, like a rubber pad, underneath that stand, and then that rubber pad sits on the concrete housekeeping pad, something like the sketch that I'm doing here. So those are the two major ways in which we can support a vertical inline. And then as you already noticed, the this end suction pump is supported by the frame that's over here. Any other questions, Brett?
A couple of pertaining to piping arrangements for both models. Do you recommend the same type of straight run of pipe for both, or can one be a little
so let me
tighter?
touch base a little bit on how a pump is actually tested for performance data in the laboratory. So Take-O has a Hydraulic Institute certified mechanical test lab. Boy, that's a mouthful of words.
Holy moly.
So we have a certified mechanical test lab certified by the Hydraulic Institute. And so we follow the Hydraulic Institute standards for measuring the performance of a pump. And depending on the model of the pump and the pipe size itself, the inlet, we usually have a straight run of pipe on the inlet. That's kind of connecting a straight run of pipe here. And that straight run of pipe is generally between 10 and 15 pipe diameters. And then the outlet of the pump has a straight run of pipe, same size as the outlet of the pump itself. And that length of that pipe is usually between 5 and 10 pipe diameters. Now, it depends on the size of the pump and the flow and the velocity. So that's why we have a range of lengths for the suction side. So over here on the right on this pump, that's the suction side, and this is the discharge side. Now those diameters and lengths hold true for the end suction pump. So for testing purposes in the laboratory and to establish performance criteria, that's how a pump is tested. Now, when you install a pump in the field, generally you don't have the physical space to put in, say, 10 to 15 pipe diameters at the suction. and 5 to 10 pipe diameters at the discharge. So you have a couple of choices. But keep in mind, everything that you do will tend to degrade the performance of the pump ever so slightly. In some cases, by the way, it can have a significant impact, especially if you have the entrance conditions to the pump that create unusual turbulence. The flow of the water through the pipe is what we call laminar flow, which means we can get these nice parallel streams of water. And so we have these little vectors here that represent the
Those lines are
parallel
pretty
flow.
parallel too, Rich. Awesome.
Yeah, I know it. And when you consider that that cocktail that Dave suggested,
Tacotini.
Tacotinis, yeah. So the idea is to have laminar flow where the streams are all parallel to each other, and you get this nice velocity profile entering the pump. Okay, and that gives you the best performance. Now, if you put things on the suction side of the pump, let's say you put a short radius elbow and an isolation valve, perhaps a flex fitting, that's going to create turbulence. And whenever you create turbulence on the suction side of the pump, the performance of the pump degrades. So what you want to do is you want to have the least amount of turbulence as possible. So one way that you can do that is put in an end suction diffuser. End suction diffusers actually have vanes inside of them that help straighten out the flow if you don't have room to put in the longer pipe and the long radius elbow. So the suction side of the pump is critical in terms of how you pipe it. It's tested with 10 to 15 pipe diameters. We know you can't do that in the field. So you have to recognize that the pump will degrade slightly as a function of the inlet conditions and to some extent the outlet conditions. Hopefully that answers that question.
Yep. So I have a couple other questions that I'm just going to start spewing some answers to. Is it more difficult to insulate the pump head on a vertical inline pump? I'm assuming Sean is talking about the motor. You do not, we never recommend, you should not and cannot insulate the motor. I've seen the insulation for a chilled water application for these vertical pumps done with a couple big pieces of block of insulation. It's not too bad. So that's my statement on that. What about the performance for both pumps for the same condition? That's a great question. I did some
so
study.
in a few minutes, we're going to go through some selection and we'll talk about what the performance difference might be. Back in the day, when I say back in the day, prior to January 27th of 2020, the older style pumps, let's rephrase that. The Department of Energy required that all new pumps meet a new performance requirement, which was called a Pump Energy Index, or PEI. And that went into effect on January 27, 2020. And in order for us to meet that deadline, we had to redesign the majority of the pumps that we offer today. And so the pumps are much more efficient from model to model or type to type. And there is not a significant difference in efficiency as compared to the older style pumps. So to say that one pump is more efficient than another, it might be based on your selection, but in most cases, you'll find that pump size for pump size, motor size for motor size, efficiencies are relatively much closer today than what they used to be. So there's no major advantage in efficiency of one over the other.
Onward and forward.
We ready to go?
Yes, sir.
Okay, so let me show you a couple of other model pumps. Now, these two are the most popular in the commercial line, not just from Taco, but from all manufacturers all over the planet. These are the two most popular. As we get into larger commercial pumps, we start getting into what is known as a horizontal split case, which is on the left, and our model number for this particular pump is a TA. And then we get the vertical split case, the one on the right. And these guys start going up in flows. The one on the left goes to around, this particular TA, I think it's around 6,000 gallons per minute. The one on the right goes up to about 10,000 gallons per minute. So let's talk about each one so we kind of get an idea. Similar to an end suction pump, this pump over here on the left is called the horizontal split case, and it gets its name because the motor is mounted, pump is mounted horizontally, and the casing along the pump is split along this horizontal line. You can see it goes all the way across, and although we can't see it from the other side, it continues on the other side, and you can actually split that case right horizontally along that plane. So this top section of the pump lifts right off. And similar to the end suction pump, on these style pumps, the inlet size, the inlet is larger than the outlet. So maybe, and I'm just guessing, I don't know the exact size of this, but if my pipe was on this side here, so for example, this might be a 4-inch inlet, and this might be a 3-inch outlet. I'm kind of grossly drawing the pipe over here. So the inlet might be 4 inches, the outlet might be something like 3 inches, or maybe it's 6 inches and 4 inches. You get the general idea. So there's always a difference in pipe size on a horizontal split case. Very similar to the end suction pump, it has a base. The pump and the motor is attached to the base, and it also has a drain pan. Now you can see where the pipe, you can connect the pipe and go to a floor drain. You thread that right into that fitting, and then you can connect that to a floor drain with an air gap. Always have to have an air gap. So there's a floor drain right there. That's a nice floor drain, Brett. I'm doing pretty good tonight. With
I like it.
Yeah, I know it. That's really cool. And then the void space inside here, kind of draw this out. That is where we put the grout, which is like a liquid concrete, and that provides the stiffening required to keep that pump motor frame assembly from twisting, makes it very, very rigid. So similar. And then because this is a split coupled pump, which means we have an independent motor shaft, we start getting into these larger pumps, the pump shaft and the motor shaft. There's the pump right there. And underneath this covering, the shroud is where the coupling is located. So that is called a horizontal split case, and it gets its name because it has a horizontal plane that splits the pump. And again, you can service the bearings. So the bearings are outboard here. The seals are embedded inside here, and you can unbolt the top half of this pump without disconnecting it from the piping system and without disconnecting it from the coupling or the motor, and you can service the bearings and you can service the seals. And if you have to service the seal on the back side of the pump, you can take the coupling off, take the shroud off, the coupling off, and then you can remove the bearing for the back side. And because the top of this pump comes off, you can actually pull the impeller up, vertically upward. I got too many lines in there right now.
Holy moly.
Holy moly. So yeah, this covering comes off vertically like this, and that exposes the impeller and the shaft and the bearings and the seals. So you'd be surprised. These are relatively easy, even though physically large. You can't pick up the parts yourself because they're quite large and heavy, but they're relatively easy to service and to replace things like bearings and seals. So that's called a horizontal split case. And then the big boy on the right is called a vertical split case, similar to a horizontal. And we have a horizontal plane going through here that splits the casing of the pump. You can barely see it, but there is the split right there. And you have a vertical plane goes right through here, and that splits the pump, both on the front and the rear. And so again, the pump volute, casing rather, is connected to the piping system. If you want to service the front half of the pump, you take all these bolts out and you pull all of this stuff in this direction. And you can disconnect the coupling underneath the shroud here, and then you can pull this component in that direction. Again, you might have to twist the motor a little bit, but you don't have to take the motor off of the base. So you can service the vertical split case quite easily. It's amazing, these very, very large pumps, how easy it is to service. When I say easy, I'm talking about unbolting things, taking bearings off and removing seals and stuff like that. A fairly simple process. The parts are heavy. It's not like someone like Well, maybe John and Dave and Rick, they're very strong young men, and they can lift these things up and probably do it by hand. But Brett and I can't, because, you know, I
think
mean, after all.
the term young is relative in this case, right, Rich?
Good point.
He's got a point there. So yeah, and then the same thing holds true in all of our pumps. There's this void space underneath, and that's where you pour in the grout, when the grout is a liquid concrete to stiffen the base. So we've gone through 4 of the most popular pump styles. There's a couple of other variations out there, but not dramatically. This is called a TC, which is a top connection. We have a TS, which looks almost identical to this, except the suction side of the pump is mounted on the side. So if I look at the pump from this side here, the one that you and I are looking at right now has 2 connections, one here and one here, and then the flanges at the top. This is kind of gross. I call them rabbit ear pumps.
Well, it looks like a rabbit.
Pumps. Looks kind of like a rabbit, huh? Well, we make another model called a TS. It looks just like this, only instead of the suction being at the top, the suction is down here on the side. And TS stands for side connection. So there's the suction side. And this was the other one, which I'm just kind of showing. And then the discharge is over here. So that represents, those 4 models represent about 99% of the configurations that are in the commercial pump arena. Isn't that cool? So before we get into some selection, any questions about the 4 different configurations that make up the overwhelming majority of commercial pumps that are out in the marketplace today?
One statement and one question. Our good friend Dave said he's not lifting any of these pumps. He will hold the flashlight. And
well,
we had
yeah, actually, I'm glad he brought that up, because it's important to hold the flashlight. If anybody's and by the way, one of my hobbies is I work on project cars. I have a project car I'm working on right now. Anybody out there in Audienceville well, the guys that work on cars and stuff, both men and women, called gearheads. So do we have any other gearheads out there? And by the way, when you're working on your car, isn't it the darndest thing is where the heck do you put the flashlight? No matter where I work, I cannot get the flashlight to shine on the piece that I'm trying to take off. I had to put a new alternator in my wife's car about a month or so ago. And do you think I could get that flashlight oriented in such a way that I could see the nuts and bolts that I had to take off? No way. So if I could get someone to hold the flashlight like Dave has volunteered, I mean, that's half the battle right there, right?
Megan and Sean recommended you use a headlamp. Holy moly.
Well, actually, my daughter gave me one of those, and I did try it, but you know, it's one of these things that you have to keep like moving your head around to get the light to flash in the right, to point in the right direction. It's a little bit better than the drop light or the flashlight, but yeah, it's still crazy. It's
Jim
crazy
said,
stuff.
call Dave next time. So the other, okay, let's get back to serious stuff here, if we can.
If we can, yeah.
Base mounted pumps. You're showing 2 big boys here, frame mounted pumps.
Yep.
Do pump manufacturers always recommend base mounted pumps be grouted?
We do. I can't speak for the other manufacturers, but we recommend that all base mounted pumps be grouted. The answer for us is yes. I don't know if other manufacturers call for the same thing.
I do know we were on a lunch and learn the other day, Rich and I, and one of the gentlemen that we were presenting to asked about grouting and the philosophy on that, and he did mention that they had an issue with a pump. It happened to be red, not that it couldn't have been green, but it voided warranty. It voided warranty because it was not grouted. So, Bill just stated B&G pumps is yes to grout as well. I have a feeling it's across the board for HVAC hydronic pumps. But as Rich said, we don't know that for sure, but I do believe so.
Well, you know, I have a quick story to tell. So a gentleman by the name of George Tabor was with TACO for, I think, probably 40 plus years.
He almost started it, but not quite.
Yeah,
He's
and he
not
was
100.
he was the go-to guy when he was at TACO. And actually, I think it was about a year before the COVID thing struck. George was in the factory, and we were chatting about some odds and ends things. And the story that George likes to tell is that he got a call from the customer, and the customer said the pump was moving around or was vibrating. That's the term he used. It says was vibrating, making a lot of noise. And George goes out there and he says, well, you didn't grout anything. And on top of that, you didn't level the base. You have to level the base, shim it properly, then grout it, and then bolt it down. So he goes out there and with just a hand level, he puts the level on the base. He puts some washers underneath the base, and he has the contractor pour the grout in. The grout sets up. He comes back the next day, tightens down all the bolts. Everything is aligned properly. Starts up the pump. All the noise and vibration goes away. So it's critical. It's very, very important, especially when you get into these large horsepowers. I mean, some of these pumps can go easily up to 450, 500 horsepower. So it's important. Very, very important. Good stuff.
Yep.
And
here's one other great question. Are all TACO motors frequency drive compatible? Yes. But
I believe the answer to that is yes. Yes.
Yeah.
Yep. Yeah. I think that's a standard now. That became a standard several years ago. It's been around for quite a while. But yes. Yep. The overwhelming majority of pumps that are installed today are connected to variable frequency drives. Very rarely do we see a pump that's not connected to a variable frequency drive. Good stuff. Next, Brett.
Let's move on.
Okay. So now that we've talked about the different pumps, let's show a little piping diagram. And hopefully, well, it's not all that important to see the details of this diagram. It just represents a very simple chilled water piping diagram that shows some chillers. Let me point some things while I'm chatting here. It shows some chillers over here. Here are some chillers. We have some pumps serving the chillers. Each pump is dedicated to each chiller, one there and one there. And then we have condenser water pumps, and we're going to assume that these condenser water pumps are pumping to an open cell cooling tower. And then when we get into our discussion a little bit later about net positive suction head, that's going to be kind of important to talk about. Then we also have, these are the primary pumps over here that are connected directly to the chiller. This is called the hydraulic separation, sometimes referred to as a bridge, a zero pressure bypass, all kinds of names for this guy over here. And then we have these are the primary pumps, as I said a minute ago. These are the primary pumps. These are the secondary pumps. These are the pumps that pump out to the system. And these are the condenser water pumps. I'll put CW for condenser water. And for our discussion tonight, we're going to say that this cooling tower is an open cell, open cooling tower. So there we go, open.
Hey, Rich, I just need to interrupt for a second. Someone just typed in, they can't see anything. Can anyone else type in that you can see Rich's screen? I can see it, so I can. Okay, we're getting a lot of I can. So sorry, Benton. It appears must be something going on with your computer. Take it back, Rich.
So we're going to make a selection for our secondary chilled water pumps right here. And if you'll notice, this pump is approximately 2,000 gallons per minute. I'm going to put 2,000 over here so we can try to remember these numbers, Brett, in a few seconds. It's 2,000 gallons per minute GPM, and it's approximately 40.4 feet. I'm going to round that off to 50 feet. So we've got 2,000 GPM. That's why we're going to make a quick selection here so we can start getting into some pump curve data. And we're going to call it 50 feet. That's what the system resistance is, 50 feet. And these are the chilled water pumps. And this is called a closed loop pressurized system. And we know that because it has an expansion tank over here. And this is on the chilled water side, not the condenser water side, because in the condenser water side, we said that that was an open system, open to the atmosphere. And atmosphere is sometimes abbreviated by ATM, atmosphere. At least in my career, ATM stood for atmosphere, but apparently ATM, I don't know if they did this recently. Is it automatic telemachine? When did they come out with those? Last month, Brett? I don't know. I guess they've been around.
ATMs, it might have been a couple of months
more months
before
than last
month. Yeah.
Yeah. So we have an expansion tank. I'll label that ET, not to be confused with ET phone home. Expansion. And so this is called a closed loop pressurized system. Did someone unmute themselves? Are they trying to say something?
No, you're all set.
Okay. So we're going to make a selection. So we're going to go live in real time to the TACO website. And we're going to make a pump selection, 2,000 gallons per minute at 50 feet. So hopefully through the magic of computers and buttons, we're going to go directly to TACO's website. And with a little luck, we are going to, there we are. We're at TACO's website. Oh, by the way, we just recently launched our domestic water boosting pump solution. There's a little picture over here. So if you go to our website, we have this new stuff for domestic water booster pump system. And if you have a chance to see the presentation that Rick Mayo has put together, it's really excellent and covers all the wonderful things. But that's not what we're doing tonight. We're going to concentrate on our chilled water pump for our simple piping system. I'm going to click on selection tools, just to the right of center here at our home page, selection tools. And then over here on the left, it says project builder dashboard, login required. I'm going to log in. There's my credentials. I'm going to log in so that a little bit farther down the road, I'm going to be able to use that project builder option. So all I did was go over here to the pump selection app. And now you can see, and let me zoom in. Here is our TACO pump selection app. We'll show you how easy it is to select a commercial pump. So I have, under pump type, I have 3 categories. I have either OE, these are radio buttons. I could select OE, which stands for optimized energy pumps. I could select a self-sensing variable speed pump, or I can click on this button, radio button that says standard pump. So for tonight, I'm going to select the standard pump and I put in the flow that we just talked about, which is 2,000 gallons per minute at 50 feet of head. Type that in. Now, if you'll notice, it gives us a line here that says minimum efficiency. I'm going to leave that at 0 because I want to see all of the selections that the software has to offer. So I'm going to leave that at 0. Now, step 3, under options, here is where I can put in information about the fluid. I can put in different fluid types. I can put water, ethylene glycol, propylene glycol, Shell C, and so on. And I can pick the temperature I want and then get the specific gravity. But I'm not going to do that in my initial selection. I'm going to leave the default at water at 60 degrees Fahrenheit. The RPM, I can either have all the RPMs displayed, or I can be selective, 1160, 1760, or 3500. I'm going to leave it at all because, again, I want to see what the software is proposing. If we are selecting an electric motor for North America and most of Latin America, it would be 60 hertz. In other parts of the world, for example, in Asia and the Middle East and Europe, it's typically 50 hertz. But for tonight, I'm going to leave it on 60 hertz. We're going to leave it with US units. And since I'm making 1 pump selection, I'm just going to leave the number of pumps at 1. And I'm not going to select this box over here, which says show NOL. NOL stands for non-overloading horsepowers. I'm just going to leave that unselected. And here's where I get to choose one of those pumps that we talked about earlier. And remember what we said? We can choose from end suction, vertical inline, horizontal split case, or vertical split case. These other categories down here, inline circulators, are usually for the smaller pumps. There are some models in here that cross over between smaller systems and mid-size, if you will, commercial systems. But for tonight, we're just going to look at one of these 4 categories. So what I'm going to do is I'm going to, because my flow is 2,000 gallons per minute, I am going to select FI. I'm going to select KS. There's that TA model that we talked about, and TC. I'm selecting all 4, one from each of the major categories, just to see if the software has pumps that will meet those criteria, or that criteria of 2,000 gallons per minute, 50 feet. So the next thing is to do is click on search and see what the software comes up with. Holy smoke, Bullwinkle. We got a lot of pumps to choose from. So I'm going to scroll down. You see there's a lot of pumps to choose from here. So I did that because I wanted to show you that we do have some FIs in there. We have TAs, we have KSs. Did I pick KS? Yes, KS. And also we've got some TCs. They're all in there. So each category of pump could potentially meet this design criteria of 2,000 gallons per minute, 50 feet of head. But for now, I believe what I'd like to do is select just one to kind of narrow down the searches. And I will go back later and pick a different one. So I'm just going to ask the software to just show me the FI frame-mounted pump. Click search again, and now it's just going to show me the FI frame-mounted pump that's going to do the job that I want it to do. So the very first one at the list, I can see the thumbnail, and I don't know how crisp that picture is out in computer land, but on my computer, it's very crisp. I can easily see the pump curve, I can see the system curve, and I can see the shape of the curve by looking at this little thumbnail. But before I click on that, excuse me one second, Brett.
Yep.
Before I click on that, I just want to show you that each one of these headings has, you can sort by them. So right now it defaults to EFF, which stands for efficiency, and we have a down arrow, which means it's sorting these pumps from highest to lowest efficiency, 86% down to 64%. If I click on that heading, it changes the order. See that? Isn't that cool? And I can do that for any one of these categories. So if I wanted to search for net positive suction head required by the pump, I could click on that. I could click on horsepower. I could click on speed, RPM. But I'm going to leave it at efficient, and I'm going to select the highest efficient to the lowest efficient sorting order. So before I go into the actual pump curve, Brett, do we have any questions as to how I got here?
No, pretty straightforward. You know, there's always a couple of people ask the question, which, and then maybe we'll answer it later, which model, which type do you recommend for which application? But anyways, that question's lingering out there. Whenever you want to answer it, feel free.
We'll try to answer that a little bit later as we get kind of into the pump curve itself. So I'm going to click on the thumbnail, and that's actually going to give me kind of information in 2 general categories. This first grouping, which I'll put this big bubble around, I refer to this as the narrative data. So this is not graphical representation, it's narrative. And then the actual pump graph is down here. And I know you can't see it very well, but in a minute I'm going to click on that so we can focus in on that. So I'm going to refer to this as narrative data and down here as the graphical data. But I'm going to look at the graphical data first. So let's erase those bubbles, go back here. But before that, I want to zoom in because I am going to refer back to this graphical data. Oops, I went the wrong way. In a few seconds, actually in a minute or so. So the first thing I want to do is go to the graphical data. If I click on the pump graph, I get a much larger one, much crisper and easier to read. So let me kind of center it on the screen. So here we go. Here's our pump performance curve. And we generate this information in our test lab, Okay, so whenever I look at a pump curve, I immediately divide the pump curve. So let's define what we mean by pump curve. This red line here that I'm pointing to is the performance curve based on the design criteria that we just selected, which is 2,000 gallons per minute at 50 feet of head. So it crosses that 50-foot line. And let's talk a little bit about these units. So in the horizontal axis, that's flow in gallons per minute. That's volumetric flow, and that's pretty straightforward and easy to understand. This value on the left, this is the differential pressure across the pump. And in the pump world, we use the term head, and head means differential pressure. And we're measuring that pressure in feet of water column, but we don't actually put the letters WC. I'm going to try putting a W on the side over here, Brett. See if I can actually draw that.
That's pretty good. That's a good W. Not bad at all.
Not bad.
Just I turned my head horizontal. I can see
pressure is head in feet of water column, and head again means differential pressure. That's the pressure across the pump. In our little design diagram, we said we needed a pump that was approximately 2,000 gallons per minute with a differential pressure of 50 feet to overcome the system resistance. And by the way, this blue line represents the system resistance or system curve. So now we have a couple of quick definitions. The red line is the pump performance curve. The blue line is the system curve. The units at the horizontal axis of flow in gallons per minute, abbreviated many times as just simply GPM. That's not the best G in the world. GPM. And the differential pressure in the pump world is always displayed in feet, head in feet. And again, head means differential pressure, and feet implies feet of water column. So before I get any further, let me draw a water column here. Here's a column of water. Let's just assume that we have this glass tube, and this glass tube, not drawn to scale, is filled. Let's try going over here and changing the pen color. Yeah, let's assume that it's filled with water roughly at this level here. There's a water level. And let's assume for a moment that the height of this column of water from our level to the very bottom is 2.31 feet tall. That's the vertical distance, 2.31 feet, FT. And that's the vertical height of this column of water, okay? And if I should put a pressure gauge right at the bottom, and that pressure gauge was reading in the units of pounds per square inch gauge, it would read 1 PSIG.
That's what Doug typed in, 1 PSI. He didn't put the G in.
PSI, I'm not going to have space for my G. Well, oh God. So my pressure gauge, if it was reading in the units of pounds per square inch gauge, would read 1 pound per square inch gauge pressure for every 2.31 feet of column of water. So that's where that term comes from, water column. So it's just another way of representing pressure in a hydronic system. So when it comes to the pumps themselves, rather than saying the pressure differential across the pump is in pounds per square inch, we say that it's in feet of water column. Now, just for the fun of it, let's just, we use this little circle with a triangle in it when we show one-line diagrams manually for pumps. So there's our pump, pumping from left to right. In the field, I'm not going to have the same units I have over here, but this is just an example. If I put a pressure gauge, generally speaking, the pressure gauges that are connected in the field measure the pressure in pounds per square inch gauge. So let's assume that the discharge pressure for a moment was 40 PSIG and the suction pressure was 30. Let's see how well everyone's paying attention. 30 psig on the suction side, 40 psig on the discharge side. I've made the math extremely simple. What would be the differential pressure in pounds per square inch? The differential pressure. Anybody can type that in, and you can tell me, Brett, if anybody got it.
30 plus 40 is 70.
No, it's the difference. So it would be 40.
Many people have typed in 10, but somebody went ahead and typed in 23.1.
Well, it's actually 40 minus 30, which is 10. I said in pounds per square inch, PSI. By the way, if you'll notice, this is an engineering little thing here. When I'm talking about differential pressure, I can use the units PSI for differential pressure. When I'm talking about gauge pressure, I would put PSIG, but whenever I take the difference in pressure, I can always express that in just PSI. And how many feet would that be? Well, it would be 10 times 2.31. And did you say somebody already wrote that down, Brett?
Yep.
Yes.
Ali.
So 10 times 2.31 is 23.1. So if I had a pump that I was in the field and I was measuring the pressure differential in pounds per square inch, I would take the discharge pressure minus the suction pressure and then multiply that difference by 2.31, and I would find out my pressure in feet of water column.
There's a big assumption in your little sketch there. There's a gauge on both sides of the pump. That's a big
That's kind of an inside joke, because Brett and I are also, one of our responsibilities is to do some troubleshooting when there's a problem out in the field, and we can't tell you how many times we go out in the field, there's no gauge, either on the suction side or the discharge side. So yes, we recommend that you specify pressure gauges to be permanently installed on the suction side and on the discharge side. Now, we recommend, by the way, that you use 2 gauges, and there's a method to my madness, but one for the suction, one for the discharge. I'll tell you a little bit later. Maybe somebody will give that some thought, come back and ask me, well, why do you use 2 instead of 1? So, but anyway, 2 gauges. Any questions about some of the notes that I put on here? I'd like to erase this because I have a lot of information on here.
No, you're in good shape.
We're in good, what's that phrase goes? You're in good hands with Allstate.
There you go. I have a question about the system curve, but I'm going to let you get to that first.
Okay. So let's go back again and look at some of the information that's displayed here. So again, I always go back because I want to refresh everyone's memory here. This selection is for 2,000 gallons per minute at 50 feet, and where those 2 points intersect on the pump curve right here, that is called our design operating point, all right? And again, the red line represents the performance curve, and if you'll notice, the red line is drawn between, these numbers are impeller diameter. So this black line up here shows the performance for a 12.5 inch diameter impeller spinning at 1160 RPM. And this other black line is the impeller diameter of 11.5 inches, spinning at, that's this guy right here, again, spinning at 1160 RPM. But in order to meet our design criteria, we would have to have an impeller whose diameter is greater than 11.5 and less than 12.5. Well, the difference between these 2 black lines here is 1 inch in impeller diameter, and ours is not quite halfway. So I'm guessing that our impeller diameter is a little bit less than halfway. So halfway would be 1/2 inch, be a little bit less than 12 inches. So let's go back. How does that phrase go? Go back to the future. That's what we're going to do tonight. Then go back to the future and go back to the narrative data and see what the software said. It said, oh, there it is. The software said that the impeller diameter should be cut to 11.95 inches. And I kind of estimated that by looking at the graph. But the software is much more accurate than what I can see on the graph. So I'm going to go back to my graph here in a second. I'm going to go look at that. So we're saying that this is approximately 11.9 inches, just under 12 inches. So we get the impellers. The impellers come off the shelf. I'll use that word. They're stocked on our shelf, and they come off the shelf at the full trim, which means they're 13.5 inches for this particular pump. And we take that impeller and we put it inside a lathe, and we actually cut the outside diameter down, in our case, from 13.5 inches to what the narrative data said, 11.95 inches. And when we put that 11.95 inch diameter impeller inside the casing, bolted all back together, connected to the piping, we spin it at 1160 RPM, that will produce the performance characteristic represented by this red line. Isn't that exciting?
Holy moly.
Holy moly. What was it, Bullwinkle? Bullwinkle the Moose? Rocky and Bullwinkle. Isn't that what Bullwinkle used to say? What did Bullwinkle say? Hokey smoke, Bullwinkle. No, that was what Rocky said.
Half our crowd have no idea what Bullwinkle, who the Rocky and Bullwinkle are.
Yeah, well, I bet John knows.
No doubt about it. I got to get another hat.
I bet you John has somewhere in one of his closets, he's got a hat with the little Bullwinkle antlers on it. Okay.
I'll tell you about my pajamas sometime, but not tonight.
All right, so when I first look at the performance curve, in this case, the red line for our particular design criteria, I break the curve into three parts. I kind of draw, using my imagination, I don't actually have to draw it. I create like three bubbles, one on the left, one in the middle, and one on the right. And in general, when I make a pump selection, I want to try to make my selection as close to the center bubble as possible, and to the right of this value over here. This value is the maximum efficiency at the maximum impeller diameter, spinning at 1160 RPM. And that maximum efficiency is called the BEP, or the best efficiency point. BEP, best efficiency point. And I want to select my pump just to the right of BEP in a commercial pumping system that's using variable frequency drives, in other words, variable speed pump, in a two-way valve system. Because when the valves, this guy here, this blue line, this is called the system curve, and the system curve is based on our original design criteria. I keep circling these numbers, but 2,000 gallons per minute at 50 feet. That's our design operating point, and wherever the system curve intersects the pump curve, that's where the pump is going to operate in that system. But initially, when all the valves are open, this system curve is called a static system curve. But as the two-way valves begin to modulate close, the system curve actually bends upwards to the left. I'm going to draw another system curve. And you can see what happens here. As the valves close, the pump actually gets more efficient. So it's out here, it's sitting on top of the 86% line. If I move over to this guy right here, it's a little bit higher than 86, maybe 86.1, 86.2. So you can see that as I move from this position, as the valves close, the system curve actually changes or moves, and the changing system curves, that's not a bad one that I drew just now.
No, that's that's awesome.
That's two good ones in a row. We say that the system curve is dynamic, which means the system curve is constantly changing as a function of valve position. So recapping, whenever I physically look at a pump curve, I break it into thirds. I decide that I'd like to have the center third, and that's where I'd like my selection. So getting back, I'm going to go back in a moment. Well, I'm going to erase this. Now, any questions before I erase this, Brett?
Actually, yes. I'm going to paraphrase this question. Is the system curve how's that developed? Is it a tested value? Is it mathematics? Where does that come from?
Well, the system curve is a mathematical estimate of the system resistance as the fluid flows through the pipes, the equipment, the valves, the fittings. and it represents the pressure from the discharge side of the pump all the way through the system back to the suction side of the pump. That's how much resistance the fluid is going to run into as it flows from the discharge side of the pump all the way back to the suction side. So the system resistance, which is represented by that blue line, represents the relationship between flow and pressure as it flows through the system. So the system, or the pressure that the fluid loses as it goes through the system, has to be made up by the pump. So whenever the pump matches the system, that's where the two curves intersect. That's where it's going to operate in the system.
It's a mathematical equation, right?
It's an estimate based on mathematics, yes.
Right. And then there's a statement here from John's good friend Dave. The Superman PJs?
Superman.
No, now we have to bring that up. Let's
Never
just
mind.
leave it at Bullwinkle pajamas and move on, shall we, please?
Yes.
System curves, focus.
There you go.
Focus. John, does that mean you want me to send your pajamas back to you because I can't use them anymore? Okay. Oh, so we did talk about the maximum efficiency. That's that 85 point. So I'm going to repeat it up here. The best efficiency point in this case is 88.5%. 88.5%. And for every pump manufactured in the planet, there is only one best efficiency point, and it only occurs at the maximum pellet diameter at the design speed, in this case 1160 RPM, and in this case it's 88.5%. That is called the best efficiency point, 88.5% in our case, and that tells you that's the greatest amount of efficiency that this pump can produce. Anything other than that value is going to be less. Any place on this curve, no matter where you select it, unless it's right at that design operating point, the efficiency is going to be less, because this is the best it can possibly be. Best efficiency point, or BEP. A BEP is a number that all pump manufacturers publish. So they either call it out, they actually have an arrow that points to it and says BEP, or it's implied, like it is on our curve here, where you can see that it only occurs at the maximum pellet diameter, in our case 13.5 inches, and it's the maximum efficiency as we slide up and down the pump curve. So that's a very important value called a BEP, and allows you to compare one pump against another. Typically, the higher the BEP is, the higher the rest of the efficiencies are on that particular pump model. So it's a good way of comparing pump A to pump B. Okay, before I go on to the next piece of the information on the pump curve, any other questions, Brett?
So all system curves look the same from pump to pump? Kind of,
Well,
right?
as long as it's a closed loop pressurized systems, all system curves start at 0, 0. Closed loop pressurized systems, and then they go up like they shape here, they have. If the system resistance is less than anticipated, then the system curve would start at 0, 0 and come down here, and where that system curve crosses the pump curve, that's where it would actually operate in the system. So in this particular case, if somebody had actually calculated 50 feet, but in reality it was something less than that, let's just kind of, I'll draw a little circle. Well, let's just say it's let's say it's just under 30 feet. What is that value there, Brett? That's 20.
2, 4, 6, 8, 10.
8, yeah, 20. So that's 28. It's approximately 28 feet. So it's crossing the 28-foot line right there. So if the actual system resistance was 28 feet, then we would say, well, the system curve is at 28 feet and 2,000 gallons per minute, but it crosses the pump curve up here. And so this is where it's actually going to operate in the system. Isn't that cool?
Yep.
Okay. And we're running a little bit longer than I had anticipated, but how are we doing
Not
out
9
there?
o'clock yet.
It's not 9.
No. It might be 9 someplace, but not
Yeah,
in the East Coast.
Okay, so we've gone through how to read a bunch of stuff, wonderful stuff on the pump curve. let me erase this. And there's one other, oh, there's a couple of other values. These dotted lines right here represent lines of constant motor horsepower. So this is the line that represents a 15 horsepower motor, a 20 horsepower motor, and so on, all the way up the line until we get the maximum horsepower that this pump can be fitted with, which is a 50 horsepower motor. And so our design operating point, if I can kind of just continue this dotted line here across here, that's 30 horsepower. And our pump is just below the 30 horsepower line. So that means if I go back to the narrative data and I look at what the software predicted, should be just under 30 horsepower. It says the horsepower is 29.26. So there, look at that. I got pretty close, just under 30 horsepower. So that's how much horsepower the pump is going to consume from that motor. However, there's always a however in our business. If I follow the pump curve all the way down, if you'll notice the pump curve crosses as I get farther down here, crosses the 30 horsepower line. So the maximum amount of power that this pump could possibly consume with an 11.95 inch diameter impeller spinning at 1160 RPM is just over 30 horsepower. And we call that the non-overloading horsepower. There's a mouthful for you.
Holy
The
moly.
non-overloading horsepower is just over 30. We actually have it in narrative format. It's 31.51, which means that I need to select an electric motor that's greater than 31.51. So I go over here to motor horsepower select, and you can see I want a 40 horsepower motor. That's the next one up incrementally. That means that that electric motor will be non-overloading over the entire pump curve, and the maximum horsepower that that pump could possibly consume is 31.51 horsepower. So that's what non-overloading horsepower means. It means the maximum horsepower that that pump could possibly consume. A couple of other lines to call out. If I draw a line vertically upward from 2,000 gallons per minute, and I go to this chart above, you can see, whoops, that's not the greatest. Try it again. There it is. It crosses approximately just under this line here. So that's 0, 5, 10, 15, 20, just under the 10. So I'm going to say that that's 9 feet, 9. And we have a special name for this one. This pressure is actually in feet of water column absolute. This is absolute pressure, and the name we have for it is the required net positive suction head. Required net positive suction. So Brett, I think we're sort of running out of time here in terms of our main presentation. We've covered a lot of material. I'm happy to keep going. How are we doing? Is our audience hanging in there?
Yeah, I mean, we've only lost a couple, so I think so. And we're still getting some questions. We got a couple questions hanging out there.
Yeah, let's try a couple of questions, and then we'll go on to the next piece of information.
Well, okay. I'm going to throw this one out there to everybody. Do all pump manufacturers have similar BEPs? No, TACO has the highest BEP. Oh, I'll let you answer that, Rich.
Yes, actually, it turns out that I believe the statistics we got from our engineering group is that our best efficiency points are higher than 65% of all the pumps that are manufactured in North America today. There's a mouthful. That our BEPs are higher than 65% of the pumps that are out there today. That's impressive. We had gone through a fairly rigorous period of redesigning our pumps so that they would produce a substantial efficiency. So yeah, I mean, some of our pumps, you can see this one here is almost 90% at its BEP. That's amazing. You know, if you look back, and in fact, when it comes to replacing pumps, a lot of times we'll get a call from someone if they've got a pump that's say 10 years old, and they'll say, well, look, I want to get some parts so I can rebuild this pump. And we'll say to them, gee, you know, you might want to consider putting a new pump because your pump, you know, built 10 years ago may only be 70% efficient. And in this case, this one has a maximum or best efficiency point of 88.5%. When you consider the increase in efficiency and the reduction of power consumption is dramatic And in many cases, you can actually pay for the replacement of the pump in efficiency savings alone in sometimes less than 2 years. Not all the time, but sometimes less than 2 years. So that's really cool stuff.
I have a question that's one of your favorite questions to hear. Well,
Okay.
it has to do with NPSH. Does a closed loop system have to deal with NPSH?
Under certain circumstances, the answer is yes. The answer is yes. NPSH, net positive suction head required by the pump, by definition, NPSH is the absolute pressure above the vapor pressure. So we start to get into a little bit more science. If we have a little time, we'll touch base on that. But basically, when we talk about water especially, it does apply to other fluids, but let's just talk about water since that's the fluid we're talking about in this system. If you reduce the pressure low enough, that water will begin to boil. So at atmospheric pressure at sea level, anybody want to type in what they think the atmospheric pressure in pounds per square inch absolute is at sea level, the number that we use? Anybody type in any numbers, Brett?
14.7, Christopher said. Timothy,
Yes.
Abe.
14.7 pounds per square inch absolute. That means that water at atmospheric pressure, if I put water in a pot, and put it a pot on the stove, not the pot you smoke, the pot, the metal one, Brett.
Yep.
And you heat that water up, and if it's at sea level, it's just clear water, that water will begin to boil at 212 degrees Fahrenheit. Isn't that cool? If I put it in a closed container, sealed container, and I evacuate the air and I reduce the pressure, it will boil at a lower temperature. So here's the thing. If I have a hot water heating system and I have a hot water pump that's at the top, the very, very top of the building, and my temperature is high enough and my pressure is low enough at the suction side of the pump, I do have to worry about not having enough pressure, because if I don't have enough pressure, here's where all the fun stuff, the pump will cavitate. So if the available pressure is less than what's required by the pump will cavitate, and cavitation will destroy a pump in a relatively short period of time. So yes, in a closed loop pressurized system, if the pump is at the top of the system, the very, very top, and the temperature is high enough and the pressure is low enough, that pump will absolutely cavitate if the required pressure by the pump is greater than what's available pressure. So we actually had one, well, now with COVID, I always lose track of a year. It's about 4 years ago, exact same situation, pump at the top of the building. The pump had a required NPSH of 40 feet, and the system only had 20 feet available, and that pump cavitated. So yes, under the right circumstances, in a closed loop pressurized system, you do have to worry about an NPSH, because if it's not correct, it will cavitate. Cavitate will destroy the pump.
We have a great question from Troy, because not everybody probably takes this into account. Is PSI gauge, such as discharge on the discharge side, is located at a different height? Do you have to take this into consideration? I kind of messed that statement up, but I think you got the gist of it, Rich.
Yeah, so if I look at the end of an end suction pump and I have a pressure gauge, and there's my discharge, and I'm looking at the end of the pump, there's my suction. And I'm going to exaggerate for this example here. If the elevation here is, say, 10 feet, and the distance from the suction, the vertical distance change, and this is 11 feet, then I do have to make a correction for the vertical height when I take my measurements. In an inline pump, I don't have to do that because the suction and the discharge are at the same elevation. So the height difference here is 1 feet, and I have to make that correction when I'm measuring in the field. Hopefully that answered that question.
Yep. And by the way, our inline pumps, KV, KS, and our base mounted FI and CI have pressure gauge ports available to be used right on the pump. So that is something that's available there.
Yeah, so if I have a pressure gauge at the flange connection here and the flange connection here on the suction and the discharge. The other thing that you have to correct for in an end suction pump, remember I said that the inlet is larger than the outlet? You have to make a correction for the change in velocity. Because if the outlet is smaller, I'll have a higher velocity, and so I have to make a correction for not only the elevation difference, but the velocity difference. All these fun things. We make these corrections, by the way, when we publish the curve in front of you, we've already made those corrections in the laboratory. We make it for the difference in height between the suction and the discharge, the velocity difference, and if required, for the, I just forgot what the hell I was going to say. I'll come back.
That's close enough.
Close enough for government work.
Here's another good question. Here's another good question about
I love these
applications.
questions.
Yeah, no, this is great.
Actually, I was just checking
we
on the
asked and we're
checklist.
receiving, right? So
we covered nearly everything on our list here. We have a couple of things hanging out there, but yeah, these are great questions. Go ahead.
So here's a good one. Applications, right? The question always comes up about applications, and you showed some selections at different speeds, right? 1200, 1800, 3600. When do you use which one? What's your recommendation on that?
Well, so here's the thing, is that the faster the pump spins, the shorter its life expectancy is. It's kind of like, if you have a car and you drive it around all the time at 30 miles an hour, it'll last a lot longer than if you drive it around at 80 miles an hour. If you drive it around at 80 miles an hour, you go around curves, the tires wear out faster, the motor wears out fast, everything wears out faster the faster it runs. So that same thing holds true for pumps. So the slower the pump rotates, the longer it will last, especially these larger commercial pumps. So that's number one. Number two is noise. The faster the pump rotates, the more noise it makes. Now, this particular pump that we're selecting is 1160 RPM. And for our commercial pumps, there are always 3 speeds that are available: 1160, 1760, and 3500. So a 1760 RPM pump will make more noise than an 1160 RPM pump. And also a 3500 RPM pump will make more noise than 1760 and obviously more than 1160. So if you're concerned about longevity and you're concerned about noise, you might want to consider going to a lower speed. However, the lower speed does not always guarantee the best performance for a particular pump. Sometimes the better performing pump is operating at a higher speed. So there's a trade-off between longevity, sound, and performance. And so you have to look at each individual selection to see which is the right combination for your particular job.
And 1760 motors are probably the most economical in shortest lead times, and 1200, 1150, whatever you want to call them, and 3600 are more expensive and longer leads most of the time. I would
That's
also
correct.
add to that statement.
Right.
So you think about first cost, you think about schedule, and then you think about replacement costs down the road. It all adds up as you go. So here's a question that's a little out there, and it'll be interesting to see how we answer it, or you answer it. How do you determine actual pump GPM in a working system or in the field? Put a gauge on it.
Actually, that's the number one issue for us. When someone calls up and says, hey, we've got a problem with the pump, we say, well, tell us how you're measuring the flow. And the overwhelming majority of the time, they come back and they say, well, we're estimating what the flow is. I said, well, how are you estimating the flow? Well, we're looking at the suction gauge and the discharge gauge, and then we're looking on your pump curve. And I said, well, sometimes that's good and sometimes it's not so good. So the answer really is you should have an independent, non-invasive, calibrated flow meter. There's a mouthful.
Holy.
And generally speaking, they fall into the category as what is known as an ultrasonic flow meter. It actually straps on to the external pipe and calibrated properly. Usually you need something like 5 to 10 pipe diameters before you get to the flow meter. So you do need a straight run of pipe to put in on a non-invasive ultrasonic flow meter. Non-invasive means you don't have to drill any holes in the pipe. You don't have to have any fittings. It just straps on. And a calibrated ultrasonic flow meter is generally what we ask for when someone wants to measure the flow. So yes, for permanent installations, you can have a magnetic flow meter. We actually have multiple ones in the factory back in Cranston. And so we have very accurate flow meters for measuring the flow. And we do have to calibrate them periodically to make sure that they're reading the right values. So yes, where do you get the flow? You have to get it from a calibrated flow meter. You can estimate the flow by taking measurements and pressure differential across the pump, but if you have poor inlet conditions, that'll throw off your measurements. So yes, you need an calibrated flow meter. There's no getting around it. Sooner or later, you're going to have to put one in there in order to find out precisely what the flow is.
And you know, Rich, I don't know about you, but the calls I get are never for a 5 or 10 horsepower pump motor combination. They always seem to be for the 50, 60, 75, 100 and above motor horsepower
absolutely.
combination.
Yeah, I think we had 3 pumps out in the field this week, and precisely the same issue. I believe they were 100 horsepower motors, and we actually took all the field data and we concluded that their flow meter was out of calibration. So they had to go back, and we're waiting for the results after they calibrate the flow meter. So
you know, here's a thought. You know, maybe other people have already thought about this. On our MEP drawings, on your detailed prints, maybe if the pump is a bigger one, you have a different detail that includes added components compared to another one. Who knows?
Yeah.
I don't know. I'm just talking about. So, you know, as we're moving forward with this pump curve, there's a question about, is there a possibility to show different speeds on your pump curves? So
this curve has got an 11.95 inch diameter impeller, and it's shown by this red line running at 1160 RPM. And let's assume for a moment, let me just do a quick calculation in my head. I just want to kind of think about this a little bit. And yeah, okay. So let's say that I want to look at, say, 5 different speeds and see how they perform, how they would look on this curve. I would go back.
And before you do that, Rich, a variable speed drive, correct me if I'm wrong, does not change the speed. It changes the speed, but it doesn't move on the original curve as you're going to show, correct? It actually changes the whole curve. Am I saying that correctly, or am I asking that correctly?
If the system curve is static, then the system curve will stay fixed in its current position.
Right. That's what you're going to show.
And that's what we're going to show. So I just go back here to the narrative data. And if you'll notice, I can scroll down and it says, click here for curve options. And then I'm going to go over here where it says variable speed. I'm going to click on that button. The number of curves, I said I'd put in 5. And a minimum speed, I'm just going to estimate it to be approximately 800 RPM. I'm going to leave the control head at 0, regenerate the curve, and then I can zoom in. And now you can see all the different speeds from 1160. Let me zoom out just a hair. Back in just a little.
I don't know who draws a better line, you or the computer.
I don't know. Tonight, I think I'm doing pretty good.
I know. I thought you were.
So here's the red line is at 1160 RPM, and here we have 5 different speeds. We have 1088, 1016, 944, 872, and 800. And where it crosses that system curve, that's where the pump would operate at those respective speeds. Now, that's if the system curve remained fixed or static. But in systems, the system curve actually, as two-way valves begin to close, the system curve bends upwards to the left, like we said a minute ago. I'm going to show multiple system curves. These aren't the best hand drawings in the world, but you get the general idea. And where those new system curves intersect the new speed curves, that's where they'll operate. So maybe this one is operating here, and this one's operating here, and this one's operating here. Look at all these wonderful curves, Brett. I didn't do such a bad job this time.
No, that's
So
awesome.
here,
Holy moly, that's
operating
fantastic.
here. I'm going to get a different color. Let's try green, and where if I connect all of the, and this is kind of gross connection. I'm kind of draw a line that sort of connects all of, that's not the best. That's called a control curve when we do that. So I did it's kind of gross, I know, because I drew all the system curves by hand. I drew the control curve by hand, C control curve, CC control curve. And where it intersects this y-axis over here is called a control head. Control head, I'm just going to abbreviate it, control head. So yes, we can display multiple speeds, and if you don't draw these other system curves in manually, we can't draw them in using the software. We will in the future. We're having new software. We're all excited about it. That'll be launched, I think it's being launched around the 1st of next year, but we'll be able to show not only the different speed curves, but the different system curves overlaid on top of each other. I've kind of shown it what it looks like. It's not the best hand drawing in the world, but you get the general idea. So yeah, we can display different speeds. Isn't that cool?
Yep. So what's your recommendation? How low would you let the variable speed drive go down? 30%, 60%,
that's a great
20%?
question. So the general guideline is that at the best efficiency point, that's at 85%. If I drop a vertical line all the way down here where it intersects the horizontal line, I think that's 21, 2, 3, 4, 5. Yeah, that's 2,100 gallons per minute, 2,100. If I take approximately 20% of that value, so 2,100 times 0.2, that means that my minimum flow would need to be around 420 gallons per minute. So if this is 0, that's 1, 2, 3, 4, 420, and that intersects this control curve over here, so that I would have to have a slightly slower, I could probably go down to maybe 775 RPM. Now, maybe not quite, maybe 790 RPM. So the slowest I could run this pump is 790 RPM to ensure that I had a minimum flow, which is about approximately 20% of the flow associated with BEP. There's another mouthful, huh? Good stuff.
So here's a statement / question comment. As the variable speed drive slows the pump down, is the pump less efficient?
Great question. No, when you change the pump speed, the efficiency rate remains relatively constant. These efficiency lines that are displayed here are for different impeller diameters, But if you fix the impeller diameter, then the efficiency rather runs parallel to the system curve. In other words, if this efficiency point is 86%, then that 86% is running parallel to the system curve over here. So if we started with the crossing the pump curve up here, and that efficiency is 84%, then it would run down parallel to the system curve and be constant at 84%. So the efficiency remains relatively constant as I change the speed, depending on where I start on the system curve.
Woof.
Woof.
So back to the curves. Can you show the rest of the attendees how glycol affects curves?
Yes. That's a really good one. Let's see. Let's erase all this stuff and go back. Jot down. I'm just going to go back here to, let's see, this is pump FI 8013D. I want to erase all those things. FI 8013D. Okay, here we go. All right. And what am I going to show again, Brett?
Glycol.
Glycol. Okay. Look at the horsepower the pump is consuming, 29.626 horsepower. I'm pumping 2,000 gallons per minute at 50 feet. If I change the fluid, I'm going to exaggerate so you can see the difference. If I change the fluid, in this case, I'm going to go to propylene glycol, and I'm going to change the temperature down to 40 degrees Fahrenheit, and the glycol concentration, I'm going to make it 50%. I'm kind of exaggerating a little. Most people wouldn't do this. Get the specific gravity, search for the pump, go back to the FI 8013D, and now the horsepower has climbed to 30.8 horsepower. And here's the performance at propylene glycol at 50%. So to pump 2,000 gallons per minute of 50% glycol at 40 degrees Fahrenheit, my power consumption goes up, and that's at the same impeller diameter. So it's the amount of power it takes to, the glycol affects the power consumption directly. All of the other data remains the same.
The bottom line is the TACO software can show you the effects of glycol.
Correct.
There's a lot of colored lines on that piece of paper. That's graph right.
Can we zoom in a little? Let's try zooming in. Yeah.
Remember the old days?
There's the same system curve that we had before. Let's go through this. There's the system curve. There's the pump curve at 11.95 inches. That's the red line. Okay. But the horsepower has gone up. This horsepower line has gone up. So where we intersect, this little diamond over here, or triangle, shows you that we're just above 30 horsepower. So that's what this line represents, just above 30 horsepower, 30.8 horsepower. The NPSH remains the same, and the efficiency remains the same. So it's the horsepower line that shifts when you change the characteristics of the fluid, because ultimately what's changing is the specific gravity. And when we talk about horsepower, horsepower in a pump is a function of flow, head, specific gravity, and efficiency.
And next week we're going to make sure everybody realizes how important considering glycol is for expansion tanks.
That's
Stay
right.
tuned for that one.
Yeah.
So I forgot what I was going to say. Oh my God. So Mike says, and I'm not sure, maybe you can understand this one. Many jobs are single pump systems where pump is down. Then BTU out divided by 10,000 with a bunch of question marks. I forget when he posted that. Is he trying to calculate something? Does that make sense?
What was the, I'm not sure I understand the question. Try me again.
Yeah, okay. Many jobs are single pump systems where pump is down. All right, so now you don't know anything about the pump, I guess. Then BTU out divided by 10,000. What the hell is that? That's confusing.
Well, if you take the BTUs and you divide it by 10,000, the assumption there is that you have a 10-degree delta T system.
Right.
And so if you take BTUs per hour divided by 500, 20-degree delta T, I apologize. If you take the GPM, the BTUs per hour, and divide it by 500 and divide by 20, so 20 times 500 is 10,000. So if you have the BTUs per hour, you divide by 10,000. If you have a 20-degree delta T system, that will tell you what the maximum GPM needs to be at the design capacity of, in this case, would be probably a heating system, because most heating systems are sized, I shouldn't say most, many are sized on a 20-degree differential. So in other words, they have a supply water temperature going out at 180, a return water temperature coming back to the boiler at 160, that's 20-degree delta T. If you knew the output capacity of the boiler and divided that by 500 times 20, or divided by 10,000, move the decimal point 4 places to the left, then you would find out what the GPM is. I hope that's the question they asked. If
Yeah,
they
I'm
didn't,
pretty sure.
I gave you an answer for a completely different question.
Mike's still on, so if it's not, all right. So it's getting late. We may be losing people, but
Yeah.
Mike said yes. So yeah, you answered his question. So
Good.
guess what the next question is? Can this software show parallel pumping or more than one pump?
Yes, it can. So let's assume for a moment, we're going to deselect the FI just for the fun of it. And let's assume that we had 2 pumps, each running at 1,000 GPM, 1,000 GPM. So in our case, we have 1 pump running at 2,000 GPM, or 2 pumps accomplishing 2,000 GPM. So run 2 pumps. And let's make it a different one just for the fun of it. Let's do a KS in this case.
And by the way, Rich, we do have some guests on from north of the border. And, you know, in the United States, I would say it's 65-35, maybe 60-40 base mounted to inline pumps. North of the border, it's probably reversed, if not more. It might be 75-25 inline pumps to base mounted. Is that good, bad, or indifferent? Is it because of Armstrong being in Toronto? I don't know, but I'm just making that statement to the world. Back to you.
So what we've done this time is we've picked 2 pumps to do the work of 1 pump. And so each pump is going to contribute 1,000 gallons per minute, 50 feet. And here is a parallel pump curve. I'm going to pick this one here because I want to demonstrate something. So, and I'm going to click on the parallel pump curve and zoom. Which way am I going to zoom here? Is this, oh, wrong way. Sorry. That's pretty good, actually.
I like it.
So here are 2 pumps running in parallel. The way we display this, let's do this. This curve here represents 2 pumps operating in parallel, and we designate that by using the terminology P1 plus P2.
So when you define, I just want to make sure everyone understands, when you make the statement operating in parallel, that means they're both running at the same time, correct?
Both running at the same time. That's precisely correct. And halfway between 40 and 60 was 50. This is our original design operating point of 2,000 gallons per minute and 50 feet of head. So this is our original system curve, same system curve as before. There's our design operating point of 2,000 gallons per minute at 50 feet of head. And if you have 2 pumps running, we designate that this is the curve that represents 2 pumps running, and we show that as P1 plus P2. If you have 1 pump running, just 1, you shut off one of those pumps, this curve represents a single pump running, and that single pump is designated by P1 comma P2. There's that New England accent, Brett, comma. Should I say it
You
again?
and your
Comma?
comma and water. Oh,
Water. Water and comma. Okay, so there's P1 comma P2. It's a slight differentiation, but please be aware of that. So we designate as either P1 or P2. That's what this curve represents. And this one over here represents both pumps running. So when you have 1 pump crossing the original system curve, I'm going to label the system curve as system curve A, letter A up here, where that 1 pump crosses that original system curve, that means that a single pump operation is satisfactory for this particular pump. And it shows it down here, 1 pump operating at roughly 1565. So if you can drop a vertical line down here, you can see that's 1600, so it's 1565 GPM at 31 feet. So it crosses that line. You can see over here that's approximately 31 feet. Let me get my pen. I want to get another color. Go back to red. So that's approximately, what did I just say? Approximately 31 feet. So that's 20. These are 1, 2, 3, 4,
They're
5.
fours. They're fours.
Oh, golly. 24, 28, 32, 31 is approximately here. That looks right to me, right? That's
Yeah.
approximately 31. And then 1565. So that's two pumps operating in parallel, either with two pumps running or one pump running with the original system curve shown up here, which is what we showed before. Pretty cool, huh?
The bottom line is the software can show it.
Software can show
Tell you,
it.
this selection software, this app that you can put on your phone, on your whatever those other handheld devices are, or your computer, looks pretty easy to use. There's really no reason to not consider TACO as the basis of design. Oh, I shouldn't have said that. I apologize. I shouldn't add
No,
that
I
in at
mean,
9 o'clock.
when you use it a few times, it's actually real easy to use, and you can do all
Yeah.
kinds of fun stuff with it.
You know what though? I would like to mention to the folks out there, in all seriousness, if you get involved with a more complicated parallel pump design, because Rich and I have been through this. Rich has been through it just recently. You know, get your TACO rep involved, or contact Rich or myself. Because there are some idiosyncrasies, especially if you get into a more complicated one where there may be 4, 5, 6 pumps or 3 pumps or whatever. Just so that's just some friendly advice. You know, I know we all know we should know everything in this world, but sometimes it's nice to talk to others to get some friendly advice on some help on some designs.
Yeah, and I would echo your recommendation. Always contact the rep first. And if they think they need more technical support, they can always contact Brett and I or someone else that's on the team. You know, whether it's tech services or whether it's someone's from, you know, whether it's John or Rick or Dave or me or Brett. You know, go start with your rep, and then if for some reason they feel they need more support, they can always come to the factory, and we're always available, always. So
And, you
good
know,
stuff.
it comes from Johnny, the owner, president. No, he's above president now of TACO. When you call our factory, right, it's TACO-HVAC. When you call the Cranston office, you actually talk to a person. If you call during normal working hours, you talk to a person. So keep that in mind, and that's always going to happen. And they'll transfer you to another person. So anyways,
Yeah, you don't get the message. Suicide hotline, please hold.
oh man. Anyways, so parallel pumping, Rich, and I'm going to paraphrase Sean's question. Pumping, when parallel pumps, the head stays the same, but the flow doubles or increases. Is that correct?
Yeah,
Sort
so
of.
for a fixed system curve, you always have to go back to the system curve. In our case, we started off with a system curve. Here's the system curve over here. And our design operating point was 1,200 gallons per minute at 50 feet. I'm sorry, 2,000 gallons per minute, 2,000 gallons per minute at 50 feet. So there's 40, halfway is 50 right there. That's 50. I always have to relabel these. There's our design operating point, and that is the original system curve right there. And I think I lost track of what the actual question was, Brett. Help me out.
I mean the head stays the same. You double the flow. So
Yeah. So if you have one pump operating, if you'll notice, if we take this value here, which should be 1,000, and it is, it's 1,000 gallons per minute. And then at that same exact pressure, 50 feet, we add another 1,000 gallons per minute. That brings us out here to our design operating point. And if you do that at any place along the curve, so in other words, let's try this value over here. Let's try this one at 40 feet. We'll try this one, see if we can get it to work. At 40 feet, that's this value here. And what is that, Brett? That's 11, 12, 13, 1350. So
yeah, I'll say that.
1350 times 2 is 2,700. Let's go over here, 25, 26, 27. Guess what? 2,700, just like we said.
Man,
1350.
you're a good mathematician. your math comes out good.
It does tonight, and it doesn't always work out that way.
I don't know how you did that.
So yeah, at any given point on the pressure, we double the flow of one pump when we find out what two pumps are doing. This is very exciting.
So
I'm willing
what,
to hang in there a little bit longer if we have some more questions.
we have one more. We have another question. If they pop up, we'll answer them. Why does
Okay.
the table at the bottom say one pump would generate 1565 GPM? You kind of went over that, but maybe we need to clarify that.
Yeah, so what we're saying is that if you have one pump operating, this curve represents a single pump operating in this initial system curve right here. We labeled this system curve A. This has always been the system curve for all the different combinations we talked about tonight. Okay, and this tells us graphically this single pump crosses this system curve at this point in flow and this point in head. So that flow is a little over 1550, and you can see it's 1565. And the head over here is a little bit higher than, we said this is units of 4, 24, 28, 32. So 31, it's roughly 31, and there it is there, 31 feet. So these numbers here tell us what one pump is doing in a parallel pump operation. And this tells us what two pumps are doing. And graphically, it matches the data that's down here.
Parallel pumps get a little more complicated because we show static system curves, but more than likely as pumps come on and off and whatnot, that system curve's probably changing a little bit, I would suspect.
Yes, so in all of these little examples, at least in terms of this particular example of parallel pumping, I've fixed the system curve, made it static. But in reality, the system curve is constantly changing as a function of valve position out at the system. So that in the real world, system curves that are representative of variable valves actually are dynamic, and they're constantly changing as a function of valve position. This is really cool stuff.
I think we're done. Any other questions?
We run out of questions?
May we have copy of the seminar. There will be a recording sent to you, an email with access to the recording. So the answer is yes to that statement / question. Julio, can you ask your question again? He's accusing me of not answering his question. I'm not sure which one it is. We're getting a lot of thank yous. You're welcome.
Julio said, what happened to my question? Well, let's see. What was his question?
I asked, what's your, on the curve before the...
Was that the one where he said GPM formula?
On the curve before...
I think he was asking about the 30 horsepower.
Yeah, well, he was asking on the curve for the... I tried to answer it. Because the curve that you selected was just above 25 horsepower, would you use 30 or would you use the 25? Because for non-overloading, I believe was your recommendation.
I would pick an electric motor that's always greater than the non-overloading value. So if the non-overloading value was 31, I would pick a 40 horsepower motor.
Okay, that's Rich's answer. Simple enough. And that ends it.
Does that end it?
I believe. Good session, lots of information. Thank you for the presentation. A lot of thank yous. Rich, you're the most knowledgeable person I know. Oh my God, imagine that. You fooled them again.
Well, like I said earlier, that's because I make up all these answers.
It could be because you don't know a lot of people, Brett, too. Yeah.
That's true, John. Brett only knows 3 people. When you consider that Brett only knows 3 people and I make up the answers, well, that you can see why he would feel that.
Hey, I got to tell you, this was an edge of the seat kind of an event. I really enjoyed it. Thank you for putting this on, guys, and thank you all for attending and being with us. I hope you found this useful. And again, any follow-up questions that you have or anything that was unclear, please feel free to reach out to our team, and we can be happy to do whatever we need to do to help explain anything that's kind of hanging out there. We'll be back again next week. And what is next week's presentation, guys?
Expansion tanks, my very best favorite topic.
Oh yeah, all right. Yeah. We love some expansion tanks.
I like expansion tanks. They're really, really cool.
It's it's either a 15 or 30, right?
Yeah.
Oh, we're talking big stuff.
Not piss wheel. Oh, I shouldn't see.
Yeah, no.
We're leaving that out. We're leaving that out. So.
We're in good hands, honestly.
Well,
I'm going to take this opportunity before Brett closes everything down to say thank you so much for participating in tonight's TACO After Dark. It was a lot of fun for me. Hopefully you got something out of it. And like John said, please let us know if you have any additional questions and all that good kind of stuff. Brett, take it away.
Thanks, Rich. John, appreciate you sitting through it. And, Rich and I had some big shoes to fill because John, Dave, and Rick have done a heck of a job with TACO After Dark. They have quite a following.
How do I say that, Brett? They set the bar.
They set the bar. They set the bar.
Between the bar and your three friends, we did good.
You did good.
What's that game where you go under the bar? We probably did that. What's that called?
Limbo. The limbo. Doing the limbo.
We did the limbo tonight, Rich. We did the limbo.
Yeah. For us, John was very generous. He set the bar at 1.35 feet.
Yes,
oh my God!
No, 2.31 feet. That's 2.31 feet.
Yeah. One of our friends, one of our guests is saying he's in Cairo. It's 3 a.m. there, and he's sitting through it. So my God, thank you so much, Ahmed.
Ahmed, thank you so much for being with us, and I hope it was worth staying up into the middle of the night. I appreciate that.
Good God, thank you.
I don't know how you could get up at 3 a.m. We're gonna have to give you a couple of
Rich,
free cheers.
He got up. Think about it. If it's 3 a.m. now, he got up at 1 a.m. when we started, or
he just never went to bed.
Yeah, he probably was watching the late news and said, "Oh my God, these guys are going to do TACO After Dark," and sounds like the thing to do.
Well, Ahmed, thank you so much for being with us. We do appreciate that. That's great.
Yeah. You know what? All we can say is, he's got to be at work at 8 a.m. Oh, good.
Oh my God.
Catch a few winks, brother. That's.
You know what? I'm hanging up the phone. Thank you, everybody. A week from tonight, expansion tanks, and we'll have as much fun talking about that as well. John, thanks for being part of it. Dave, thanks for some of your insight. And Jim Prisby, awesome. Thank you, and everyone else. Take care, everybody. Bye.